before Wednesday. So tomorrow we'll see how class is going. We already have really the homework done and everything. We could go ahead and look a little bit ahead, a little more time on the problems that take a little bit longer. As far as due dates, 2-4 is due tomorrow night, which means your prep stuff would be due Wednesday before class or going into class. The quiz is on Friday this week instead of Wednesday. All right, any questions or anything? All right, so today I want to look at an interesting example. Y squared equal to x cubed plus 3x squared. And the goal is find points that have a horizontal tangent line. Anything strange about this equation? Yeah.
There's two variables.
There's two variables. I didn't say f of x is equal to, did I? Y squared. So like you have to solve it for y, wouldn't you? If you really wanted to think about it as a function of x. So I have multi-variables here. I don't just say y is equal to something. If you were to graph this, and we'll show this in a little bit, it actually looks like this. So there is a so what does it mean to graph a curve like this? This isn't a function. Why is it not a function? It's not going to pass vertical line test. I can't just say plug in the x value, here's the one y coordinate. That would have, so an explicit form would say y is equal to this, plug in x, you get y. What does it mean to graph solutions to an equation? So when you just say this is equal to this, we want to find all the points, all the x and y values where the two sides of the equal sign are the same thing. If I pick a random x, y coordinate pair, does it work? So let's think about the point 0, 1. Is it on the graph? So this says y is equal to 0, so, or y is equal to 1, so I get 1 squared. Is this equal to 0 cubed plus 3 times 0 squared? No, on the left I get 1, on the right I get 0. These aren't the same thing. So what does that tell me? The point 0, 1 does not satisfy this equation. So when I draw this graph, what does this graph represent? It represents all xy coordinate pairs where this equal sign holds. So one that's easy to see on here, not even labeled, what about 0, 0? Is this on the graph? Yeah. If I do 0 squared on the right, is that the same as plugging in the x value on the left? Is that the same as plugging in the x value on the right? Yes, I get 0, 0. Everything checks, that must be on the graph. All right. So our goal is, so we call this a graph for all the solutions for this. It is a graph, it's not the graph of a function. So really the way you can think of it is this implicitly defines some curve. I may or may not know what that curve is, but there could be a set of xy coordinate pairs where this equal sign holds. if I visualize them, that is graphing the solutions. So every point that is on this graph is a point where this equal sign holds. Can I draw tangent lines? So I want to know, where do I have a horizontal tangent line? You would guess right here and right here. So it looks like there's 2 points, one right here, where my tangent line would have 0 slope. Just because I have a curve that doesn't satisfy the vertical line test, does that mean I can't draw tangent lines? Like I can still do tangent lines here, right? Which means I can still talk about slope. I just can't call this a function. I can also find the tangent line right here. I can draw these tangent lines anywhere on this curve. Here I might have a vertical tangent line, which means I have in some sense an infinite slope. So I can talk about tangent lines. If I can draw tangent lines, it means I can talk about slope. What's the one problem? Do you know how to find the slope?
Find the derivative and the x-intercepts of the derivative.
Yeah, I'd have to find the derivative and then find when the derivative is 0. When I find the derivative, that's a slope question. Or that tells me the slope of the graph, but it was always the slope of the graph of a function, right? We found the derivative of a function. So there's kind of 2 ways I can carry that over to here that I want to look at. So this is approach 1. Use explicit representations, or use explicit functions. So I'm going to solve this problem the way you would have to do it if we weren't going to use any of these new implicit ideas. So we're going to do implicit second. All right, this is motivational, and it is relevant here at least. So what do I mean by an explicit function? So I have y squared is equal to x cubed plus 3x squared. Why is that not enough? Why is that not function form? What if I wanted to solve for y, what would I need? Get square root of both sides? What do you get?
Plus or minus the square root of x.
Plus or minus? I have to account for both, right? I could take y to be a positive or negative value. Does that make sense based on the graph? So plus would be this part up here, minus would be this part down here. So I could talk about f1 of x is equal to the positive square root of x cubed plus 3x squared. And f2 of x is the negative square root. And then when I put these together, I can find the y coordinate that's positive, the y coordinate that's negative. Now I have both possible y coordinates. If I get 0, like when I plug in 0 here, I get 0, they're giving me the same value. Right. So this would be an explicit form for this curve. But does that give me all the answers? So this is a function, right? Which means it's at best going to give me one of the y coordinates. I'm still missing information. So you can sometimes take a general curve like this and put it in explicit form. If it's the exact same thing, that's great. That's when we write y is f of x. There are times where you try to do that, and you can't say, oh, it's only this piece or only this piece. You have to account for multiple things. So this, in some sense, is a generalization of talking about functions. Usually when you say y is equal to f of x, you've already made the assumption this is a nice function. You have one input, you get one output. All right, so let's look at f1. So when does f1 have horizontal tangent lines? So I'm gonna solve the problem, but only looking at F1. What would I have to do next? I want to know all the answers. Also look at F2. Whatever I do for F1, basically redo it all for F2, trying to find all the answers. So, just to keep a picture in mind, F1 looks like this, and F2 looks like this. One of these is the top root, one of these is the negative root. Alright, so F1 of x is equal to the positive square root. So what's the domain of F1? This isn't necessarily where you need to start, but it's always, anytime I have a function, I always want to know its domain, just so I can rule out weird things sometimes. Well, it would have to be true. Can I plug in every number? Let's say you plug in some x value way over here, do I have a y coordinate? Doesn't look like it, right? When I take a square root, I'm assuming I'm taking the square root of something that's not negative. So my domain says I need this inside part greater than or equal to 0, right? Otherwise I can't plug in that x value. So because I cannot take the square root of the negative, I need this whole input to be greater than or equal to 0. And then if I want to solve this, the easiest way is to factor it first. I would get x squared and x plus 3. Do you remember how we did this in 1/4? That's a mean question. I'm the only one who remember that. What do we do here? We said, so like this inside part here, this is x cubed plus 3x squared. That's a nice function, right? It's cubic, nothing bad happens, which means it's always continuous. When can a continuous function change signs? Must go through 0. I can't be positive and then randomly negative without touching 0. So I'll use that idea. If I look at this part, so I have the expression x squared times x plus 3. If I plug in negative 3, I get 0, right? And if I plug in 0, I get 0. Anywhere else, I'm either going to be positive or negative. So what happens if I plug in a number way over here? I get a positive number, x squared is positive. A very negative number plus 3 is still negative. So I get a negative sign on that interval. Between negative 3 and 0, first number is always positive. Second number is, if I add 3, so take something here, add 3, it's going to move it over to a positive number. So I get a positive sign. And then if I start over here, everything's positive. So once I move past x equal negative 3, I can never be negative again. Does this look semi-familiar when we did these arguments? If not, we're going to do them pretty much for half of each class period in chapter 3. That's when we really care about this. In chapter 3, we start saying when is this function positive or negative, and we draw number lines pretty much all day every day. So again, this is just looking forward a little bit. But what would my domain be? I can't plug in a negative number, so I need to rule out all of these. So that means I could be 0, or positive, so that's all these x coordinates over here. Is that consistent with the picture right here? Yeah. If I move too far over to the left, I couldn't plug it in, right? Where there's no y coordinate. Now we know a little bit more. This is at negative 3, right, across the axis. Assuming my picture is correct. All right. We don't necessarily need this to find the horizontal tangent line, but if I get a horizontal tangent line, or we'll get to this a little bit more in a second. Alright, so how do I find a horizontal tangent line?
Could you do the chain rule on both the two functions we got? And find where they intercept zero?
Yes, so I have f1 of x is this. We're only going to look at the first one for now. To have a horizontal tangent line means my slope has to be 0, right? So I need to know the slope. How do you get slope? Find the derivative. So f1 of x is the derivative, or f1 prime of x is the derivative of this. How do I find this derivative? It'd be the derivative of, write this as something to a power. And then what can I do? It's a great section, the chain rule section. It does everything for chain rule and then implicit. It's the chain rule, right? I have a bunch of things all to the 1/2 power. So I can do the power rule. So if I did only the power rule, I would get this, right? But that's ignoring the fact that I have something inside the parentheses. So to account for the parentheses, I have to use the chain rule, which says I can take that derivative using the power rule, but then I need to multiply by this, the derivative of the inside part. I couldn't just ignore it. So I get 1/2 times this. And then what's the derivative here? 3x squared plus 6x. So I get 3x squared plus 6x in the top, divided by 2 times the square root of this. So I move the negative exponent down to make it a little easier to read. So f1 prime, I use the chain rule, I can get this. How do I know when f1 prime is equal to 0?
Find the x-intercepts of the derivative.
Yeah. I need to set f1 prime of x equal to 0 and solve for x. What is my slope equal to 0? So that says I need 3x squared plus 6x divided by 2 times all of this. Equal to 0. So you take a fraction and set equal to 0. We do take top set equal to 0. So I can factor out a 3x, and I get what? X plus 2. So x is equal to 0 or negative 2. Everybody believe this so far? If you want to figure out when something is equal to 0, these have a fraction, set the top equal to 0, solve for all the x values. And somebody's raising their hand, it's probably because I skipped over one small detail. If you look at the picture, it says at negative 2 I should get 0. Is that believable that these points happen at negative 2? And another one says x equals 0. Does it look like I have a horizontal tangent line there? At best, if I took, really I'm looking at f1 of x, at best I have a corner, right? I don't have a slope. Alright, I'll let you.
Because at 0, it's indeterminate. Because like at the bottom,
Yes.
You try to take
When
the
I said
sum
this
of
equal to 0, I completely ignored the bottom, didn't I? When is f prime of x undefined? That would be when x cubed plus 3x squared is less than or equal to 0. Where did that come from? What am I not allowed to do in that expression? I can't divide by 0. When would you divide by 0? If this whole thing was equal to 0? So if the inside part was 0, take the square root, you get 0, multiply by 2, still 0. So I can't have any of this equal to 0. Also can't have a negative, because I can't take the square root of the negative. So when does this happen? Thankfully, I already looked at this. When is x cubed plus 3x squared greater or equal to 0? As long as I'm bigger than negative 3. But then it also says it's equal to 0 if I plug in negative 3 or 0. So when does this happen? This says when x is less than or equal to negative 3 or x equal to 0. If I plug in any number less or equal to negative 3, I'd get negative or a 0. If I plug in 0, I also get 0. So I need to throw those out. Let's say you weren't being this careful. What else could you do? This is how you really catch mistakes. Or you take a multiple choice test. What do you do on multiple choice? You have your answers, plug them in. Why would you ever solve a problem if we gave you what the answers are? Just plug them in. I got 0, negative 2. What happens if I plug in 0? So f prime, f1 prime of 0 is 0 divided by 0. So that's undefined. If I plug in f1 prime of negative 2, I get 0 divided by 2 times the square root of negative 8 plus 3 times 4, which is 0 divided by 2 times the square root of 4. I don't care what 2 times, well, I know what 2 times square root of 4 is, but does it even matter? I'm not dividing by 0, right? If I tried to plug in 0, I divided by 0, that means I need to throw out that answer. I had a 0 to 0 form, that means it's not a 0, at best it's a whole. But even if it's a whole, it's undefined, right? All I wanted to know are for what x values do I plug it in and I get the top is, or what x values do I plug it in and I get 0? If I try to plug in 0, it doesn't work, I get 0 to 0, I throw it out. So usually what you do when you solve a problem, you find all the potential answers and then you throw out the ones that don't make sense. The other thing you could do is figure out when it's undefined. Well, it's undefined at x equals 0. If it's undefined here, I have to throw this value out. That's kind of like finding the domain first. The domain tells you these are the only answers you're really allowed to think about. If you get any other coordinate or value, throw it away. That's why a lot of times I like to do domain first, because it tells you these are the only answers that even make sense. Anything else, immediately discard if you find it. All right. So that was a lot of work. We got x equal to negative 2. It's the only time this happens. So the only time my derivative is going to be 0 is x equal to negative 2. And then what's y equal to? Because we said we want to know the point where I have a horizontal tangent line. How do you find points? Points are x, y coordinate pairs, right? So how do I get the y coordinate here? I plug back into here. f1 of negative 2. So square root of negative 2 cubed plus 3 times negative 2 squared. So square root of negative 8 plus 12. So I get 2. So my point would be at negative 2, comma 2. board? Yes?
The second function.
Yeah, that's only half the problem, right? Now I have to redo all of it with F2, which sounds awful based on some reactions here. Why would it not be awful?
You know, you have a slope and you have a point. and you just-
Yeah, I did a lot of work to find F1 prime. What's F2 prime? What's the only difference between these two? I put a negative sign up front. Hey, that's multiplying everything by the constant -1. What does that mean when I find a derivative? If -1 comes out by the constant multiple rule, it never makes any difference whatsoever. I just leave a -1 in front. My slope would be -1 times what I already found. So I get this, and then I can keep going and land with, again, I need x equal -2, right? When I get 0, this would be an undefined value because it'd be 0, 0. So the only time F2 is equal to 0 is if I plug in -2. Which means the other point would be my other y value is F2 of -2, which is now, I get -2, because I bring the negative out front. So really it's points, and the other one is this. Does that match the picture? This is, and now I know the y coordinate should be +2, and this y coordinate should be -2. So at these 2 points, my slope would be 0. This was using, other than the fact I drew the picture for you, really this is all using ideas we've had, including the chain rule. The one new one is when you solve for the y coordinate, you actually get 2 functions instead of just 1, if you want to break it apart. So that is, the idea here is taking this curve and trying to put it into explicit function calls. But these explicit functions can't cover every case, I have to have 2 of them. All right. So the real topic for today is approach number 2, where I use implicit. There's a 30-minute build-up just to tell you use implicit. I'm just better. We're also reviewing change. All right, so implicit is magic, which is consistent with all the reflections I read. If you decode the word magic as what in the world just happened. What's the rule when you have something equal to something? Can you just change one side randomly? What's my real goal here? Eventually I wanted to find the slope, right? What tells me the slope? Find the derivative. So the entire idea of implicit says I have an equal sign. If these 2 things are the exact same thing, then I should be able to take the derivative of both sides and they both have to equal. If this is always the same as this, the derivative of this must be the same as the derivative of this. What is that on the right-hand side?
Squared plus 6x.
3x squared plus 6x using the power rule. So really, the big question becomes, how do we interpret d dx of y squared? So, when you write d dx, this tells me x is the independent variable. So, it's the variable I care about. this is a power in terms of x cubed. So what's the derivative with respect to x? 3x squared by the power rule. But the x's have to match. So think about the chain rule. What is the derivative of u of x squared? So I have a parentheses with a bunch of stuff in it, and then x squared, or we'll make it g of x. I think that's closer to how we wrote it before. How would I take this derivative? Yeah.
Plug in the right side? Plug in the right side, maybe?
Oh, this is to motivate what I'm about to do here. So if
Power rule the entire g of x, and then multiply by the derivative.
yeah, what did I do here? Add a bunch of stuff to the 1/2 power. Just think of this as some function g of x, right? So then what happens? I do the power rule, I get all this, and then I multiply by the derivative of g of x. That was it, right? That was the chain rule. So by the chain rule, I know this would be 2 times, leave all of this alone, raise it to the first power, and then multiply by the derivative of g of x. That's believable? All right. Now, instead of calling that g of x, let's call this y. What would this become? This would be the derivative of y squared is equal to, so this becomes a y here, right? 2 times y to the first power times the derivative of y. Instead of writing g of x every time, just write the letter y. And then there's one more shortcut we take. Not shortcut, but notation. Instead of writing d dx of y, we usually write it this way. Just put dy dx. There's no reason to put the y out here to the left. You can also put it in the numerator. They notationally mean the same thing. So you believe it as a chain rule when you write g of x. Are we allowed to just replace all the g of x's with the letter y? Would this be allowed? So we always say g of x is, you plug in x value, it tells you an output. How would this work? If I tell you x is equal to 3, did you figure out what your y value is? Is there a y value? What'd you do? You plug in 3 here and then you try to solve for y? This is what we mean by an implicit curve. When I write y, when I'm taking the letter y here, this depends on x. Right? If I tell you x is equal to -10, is there a y coordinate? You plug in -10 here, you get a negative number. I can't square y. You get that? There is no y coordinate. No matter what you put in for x, it helps determine y, right? That's why when I draw this curve, there's only select x, y coordinate pairs that work. Y always depends on x in some way. I can't say here's an x value, now pick arbitrary numbers for y. Only certain numbers might work. Y depends on x. So when we do all this, when we write y's here, we're really thinking this is y of x. y depends on x. Now it just looks like a function, right?
But you can't say f(x).
No, I can't say f of x, I'm saying my y coordinate depends on x implicitly. There's some relationship there, I don't know, I don't even care what it is, there's some relationship between x and y, therefore y actually depends on the x coordinate. If I change the x coordinate, I probably change my y coordinate. I'm not telling you what that exact change is, I'm not saying here is f of x, so if you give me x, I know exactly y, I'm just saying they're based on each other. I can't detangle them.
Is y of x alone equal to the other side of the function?
So y of x squared, I mean, notationally we're saying y depends on x. So, which makes sense. If I change x on this side, my y coordinate must change. So they depend on each other, but it's not this relationship of plug it into f and it tells you exactly what to do to get to y. It's, at a high level, they depend on each other. No longer is it clear which is my independent variable or my dependent variable, right? I could tell you y is equal to 0, tell me what x is. I could tell, so it's like I'm not really specifying this is the dependent, the independent variable. If you choose y, x depends on it. If you choose x, y depends on it. There's a relationship there that I'm not even going to bother untangling. Right? So from this point of view, y depends on x. How would you take the derivative of y squared? Bring the 2 down, raise it to the first power, and then multiply by the derivative of the inside part, the dy dx part. So, and that's getting a little harder to read. The derivative with respect to x of y squared. I'm just going to, I know y depends on x, I'm going to use that idea just symbolically to say this must be 2 times y times dy dx. I still haven't told you exactly what dy dx is, but if I were to push through the chain rule, I'd have to put this term here to account for the fact I'm treating y as the inside part. So treating y like an inside variable, what is the last part of the chain rule? Multiply by the derivative of the inside. So I have dy dx times this is this. Now how did I get here? I have an equal sign. Both sides must be the same. Take the derivative of both sides. If the derivatives are the same, now what can I do? What's my real goal? My goal is to find slope, right? In that whole equation, what represents slope? The symbol dy dx. What does dy dx represent? It says the limit of your rise over run. So the slope value. And now what's the magical last step to avoid all effort? I care about dy dx. It's sitting right there. What can I do? Divide everything by 2y. These are the same thing. I can solve for the unknown. I don't know this value, so I get it by itself by dividing both sides by 2y. And I now call that my equation for the slope. I have a formula for the slope using this idea called implicit differentiation. Does this look anything like what we had before? There's one major difference. If I say what's the slope when x is negative 2, what would you do here? Just plug in negative 2. If I tell you this, what is the slope when x is negative 2, what happens when you try to plug it in here? You're still dividing by 2y. You know the y coordinate? So this tells you the slope, assuming you plug in the correct value for x and y. So dy dx using implicit is the slope at a given point x comma y. I have two inputs. And now the big one. To be relevant, both need to be on the original curve, or both need to satisfy the original equation. Alright, so how does that come into play? We'll do that real quick, then I'll have a better, or show this in more detail. So if I set dy dx equal to 0, that tells me 3x squared plus 6x must be 0, and 2y does not equal 0. Where's that and plus coming from? I need the top to be 0, but I can't divide by 0, right? If I divide by 0, my slope is undefined. So if I take my implicit, I use implicit differentiation, I got this answer for the slope. I would say this is my slope. If it's equal to 0, the top is 0, the bottom is not equal to 0. If the bottom's equal to 0, it's undefined. I can't divide by 0. We had a whole chapter on divide by 0. Nobody liked it. We don't divide by 0. We rule that one out. So what does this give me? 3x times x minus 2 equal to 0. X plus 2. So x is equal to 0 or negative 2. This one says y can't equal 0, which means y squared doesn't equal 0, which tells us what? What is my original one? Y squared is x cubed plus 3x squared. That can't be 0. It's probably nice in that when is y equal to 0, sometimes y squared is equal to 0. And hey, look, the problem I gave you said y squared is exactly this. So because I knew this formula, I can go back and do this stuff. So what happens if I plug in 0? 0 cubed plus 3 times 0 squared is equal to 0. So that's a problem. What about negative 2? So that gives me negative 8 plus 12. Which doesn't equal 0, so that one checks. So if I were to plug in 0, it doesn't. I get y equals 0, that doesn't work. If I plug in negative 2, everything checks. So the only answer is x equal to negative 2. I have to throw out x equal to 0 because of this part. So my point is that x equal to negative 2. When x is equal to negative 2, using only this part, I can tell you the slope must be 0. Am I done? If x is negative 2, do I know what point I'm looking at? Yeah. I still need to look at y squared is, so I need to go back to my original graph, right? Or equation. X cubed plus 3x squared. So y squared is equal to negative 2 cubed plus 3 times negative 2 squared, which is 4. So y is equal to plus minus square root of 4. So I get plus or minus 2. So the last thing says, if x is equal to negative 2, y is equal to positive 2, or negative 2. There's a lot of explanation to motivate it. But look how this was actually a lot less work. Took the derivative both sides, derivative the right hand side, same thing we've been doing, right? Only depends on x, just like finding a derivative. Left hand side, I had a y mixed in, so what did I do? I used the chain rule to account for it. Once I used this step of the chain rule, that derivative on the left wasn't bad, right? And then you can always solve for dy dx. when you use this trick, at the end you can always get y dx by itself. So implicit will always give me a shortcut to finding the slope. That's the one drawback. Before we found the slope, it said plug in the x value. Now I need to plug in both x and y. Do I know which y values I can plug in? That requires going back to the original thing, right? I can't just pick x and y at random. I want to pick x, y where I'm on the graph itself. So that's the hard part. It gives me a slope formula, but it may or may not be useful depending on the x, y coordinates I choose. Okay. And that's the last thing I wanted to look at real quick. So I graph this. I thought I just knew what the graph looks like. I cheated and used that much. It's called the fishtail example. It's also one that we do a lot, so we know it. If you graph, so you can type this into Desmos here. Y squared is x cubed plus 3x squared, and it plots all the points it finds that make sense. And then, where did this formula come from? X squared plus 6x divided by 2y. When we did implicit differentiation, that's the formula we got, right? This one. So I know the slope given x and y. So the last thing I do is say, okay, graph the tangent line for a given point. Well, I can take any point, right? I could say my x or my y coordinate is 3.5, my x coordinate is 1. That means I'm sitting right here. 1, 3, 5. And it gives me a slope. It would be the slope of this tangent line. Does that tangent line have any bearing whatsoever on my problem? So like I could plug in any x, y coordinate pair I want. I could plug in 1, 3.5, and this gives me a value for my slope. And then I go over here and look at where is 1, 3.5. It's sitting right here. Is that tangent to my graph? That's a completely irrelevant point of data, right? I can't just pick these coordinates at random. I have to pick the ones that land on the curve. So which ones did we say? Y equal to 2. And then x equal to negative 2. If I plug in negative 2, 2 into this equation, I get 0. And that matches what we had here, right? If I plug in negative 2, negative 2, it'll tell me my slope is 0, and I get this tangent line. So you have to pick the point based on x and y coordinates both, and they both need to satisfy the red curve, the original one, and then you can get the slope. So where's another one? 1, 2. 1, 2 looks like it's on the curve. So that is this point right here. It finds the slope, gives me the tangent line, and it agrees, right? That looks like the tangent line. So I can plug in any x, y coordinate pairs, but then if you pick random ones, it's not relevant to the problem. So when you do implicit differentiation, it will give you a formula for slope, but it doesn't tell you which points you're allowed to plug in. That's kind of the implicit behind the scenes part. When we said y depends on x, we never specified how. So that part's still kind of unresolved. You still have to know relevant x, y coordinate pairs. But once you know x, y coordinate pair, you can plug it in, it tells you the slope immediately. And it is the same slope that you would get doing it other ways. All right. So we'll finish that, or we'll stop here. Tomorrow I'll do a more detailed example with implicit.